Hey, Chemsters, this is Mrs. Vanderlei bringing you Chemster video for Chapter 5, Part 3. This is a really important section, and it's all about trends. It's all about the why behind all the graphs that you have made so far. And, in some of the homework, you're supposed to look for trends and things like that. So we're going to explain all these trends as to why things go up and why things go down on the trends that you had graphed, okay? So the basic reason for all of these trends, it's about attraction, right? It's all about attraction. So if you can understand attraction, then you can understand all these trends. My suggestion to you is not to just try to sit down and memorize all these trends. You're going to just go nuts if you do. But if you understand the attraction between protons and the electrons, then you can reason out everything that we're going to be talking about in this section. And I would think that would be an easier thing to understand the why than to just strictly memorize a whole bunch of stuff. But seriously, the only thing I think you need to memorize in chemistry are your elements, the symbols, and those polyatomic ions that are driving you nuts right now. Everything else, in my opinion, as a teacher here, that you can reason out in chemistry, or your formulas will be given to you, and it's just like, how do I manipulate these formulas? So anyway, having said that, let's talk about attraction, will you? All right. If you don't have one already, get out a periodic table to look at. That would be helpful. So pause this, find your periodic table, and then come back. All right, so here's my periodic table, and I want to think about attraction. So when I think about attraction, I think of Harrison Ford personally. Indiana Jones came out when I was in high school, and I thought he was the most attractive man on the face of the planet here. So Harrison Ford is my thing. Okay, so if you don't like Harrison Ford, insert your own picture in your own mind as I talk about Harrison Ford. So anyway, this is my periodic table. And Harrison Ford is going to represent protons in the nucleus, okay? And so on the left-hand side of the periodic table, I'm going to put one Harrison Ford. And on the right-hand side, I'm going to put a bunch of them. Let's say I put 4 of them. Why do you think I would do that? As I move across the periodic table, what happens to the number of protons? So in the first shell, I go from hydrogen to helium. I go from 1 proton to 2. As I go from lithium to neon, I go from 3 to 10 protons. As I go from sodium to argon, I go from 11 to 18 protons. So what is happening then to the number of protons as I go across the periodic table? They increase, don't they? So that's why I have 1 Harrison Ford here and 4 Harrison Fords on the right-hand side. I can't fit any more than that, okay? So heaven help me if I get, radon with 86 protons. That I just could not put 86 Harrison Fords up. That'd be crazy, wouldn't it? So then if Harrison Ford is the proton, that means I, Mrs. Vanderlei, is the electron, okay? And the electrons are mobile. They're the ones that are moving around the nucleus, so they can respond to these different attractions, okay? So if I'm over here, I got 1 Harrison Ford. That's a pretty good thing. I'm somewhat attracted to 1 Harrison Ford, but guess what? What happens as I move across the periodic table? What do you think is happening to my attraction? Holy cow, I have 4 Harrison Fords right here. What do you think is going on to my attraction? My attraction is definitely increasing. So let's try it again. I am very happy with 1 Harrison Ford. But as I move across the periodic table, what happens to the number of Harrison Fords? They go up. So what happens to the attraction? They go up. All right. So if I'm the electron, what happens to the attraction between the outer electron to the nucleus? The attraction is going up. Okay. I hope you can relate to that. I hope you understand that. So what about going down a shell? Okay, here's a different way to represent the different shells. So once again, Harrison Ford is my nucleus, isn't he? He's in the middle. And these represent these different energy shells, or maybe even talk about maybe different periods, okay? So here is my first shell, very close to the nucleus. Here's my second shell. All right, here's my third shell. Here's my 4. I can go on to 5, 6, and 7. I just didn't want to draw all those circles. And so what do you think is going to happen? Well, here I am again, and I'm at the first shell. Do you see that? I can reach out and touch Harrison Ford. I can even put my head on his shoulder. Oh, all right. So, man, I am so close to that nucleus. What do you think attraction is going to be like? Pretty high. But what happens if I'm in the second shell? Oh, dear. All right, I'm starting to get a little bit further away. What happens when I get to the third shell? Oh, dear, I'm really starting to get further away. How about the fourth shell? I can't even reach out and touch him anymore. All right, fifth shell, what's going to happen? Sixth shell, seventh shell. Man, there's like so little attraction because I'm so far away. There's also one other complication. When I am here, what's in between me and Harrison Ford? Other electrons. That's my competition. All right, there's all these cute young ladies right here in between me and Harrison Ford. I don't have a chance anymore, do I? So there's two things going on as you go down the shell, all right? Or down the group, that not only am I further away, I have all these other electrons between me and Harrison Ford being more attracted to him than me because I'm so far out here in left field. So I would be much happier right here in the first shell. That's where the attraction is the greatest, okay? And if anyone's worried, my husband certainly knows about this. I had this Harrison Ford thing well before I knew my husband, and he's just had to live with it this whole time. Don't worry. I don't think anything's ever going to happen between me and Harrison Ford in real life. Don't worry. So anyway, in case you were concerned, there's my disclaimer. Okay, so let's get back and see what this attraction has to do with these trends. Okay, so let's go back to our notes again. So let's fill this in. Attraction. As you go across a period, what happens to attraction? Remember what happened? Remember, Harrison Ford's my proton. I'm the electron. As I go across the period, the attraction increases. Why is that? Hey, baby, more protons, more attraction. All right. Yeah. All right. More Harrison Fords. Okay. Nice job. All right. That makes you pretty happy, doesn't it? Woohoo. But as I go down a group, what happens? The attraction will do what? Well, if you said decreases, you're right. Why? More shells, more distance, more competition, if you will, less attraction, and oh, I'm so sad. Look at me. All right, so that's the idea of attraction. Hopefully that makes sense to you. Okay, if not, rewind and go look at Harrison Ford again. Okay, and maybe that will help you. So now let's talk about these trends that we've been dealing with. Okay. Sorry, I had you practice this. So why don't you go ahead, pause this, and figure out which one has the greater attraction for its outermost electron. Okay, I should probably qualify that. Which one has the greater attraction for its outermost electron? So pause this, fill out number, whatever, 1, 2, and 3 here, and then come back and see how you did. Okay, go ahead and pause this. All right, let's see how you did. Well, what's the relationship between lithium and boron? They're in that same period, okay? So they're going across the periodic table. So which has greater attraction? What do you think? Boron does. Why? All right, well, they're in the same shell, so there's more protons, so there's greater attraction, okay? More Harrison Fords, you can't lose, can you? Which one has greater attraction between magnesium and barium? See, here's magnesium and here's barium. Okay, so which one has greater attraction? Well, first of all, they're in the same group. All right, so which one has greater attraction will be magnesium. Why? There's fewer shells, therefore it's closer to the nucleus. Magnesium's electrons can almost reach out and touch that nucleus. Not quite, but I think you get the idea. Way down here in barium, holy cow, that's really far away, okay? That distance makes that attraction a lot less, so that doesn't help. So what about phosphorus and what is it, strontium? So I'm talking about this and this. Folks, they're not either in the same shell, nor are they in the same group. So now what? If you have this like I say, a positive slope difference, okay? So if you're going to upwards this direction, you can still answer that question. The one that's really iffy is if you go this direction. Then you really can't say, is it the distance or is it the proton issue, okay? But in this case, it's an easy fix, okay? What is it? Which one is going to have the greater attraction? Oh, I'm sorry. They're neither in the same group or the same period. It's going to be phosphorus for two reasons, okay? You have fewer shells, oh baby, all right, and within its shell, you have more protons in it. So you can also use the transitive property because phosphorus has greater attraction than magnesium, all right? And they're awfully close. There's no thing above strontium here. And magnesium has fewer shells than strontium, all right? So you can do like, well, if phosphorus is greater than magnesium and magnesium is greater than strontium, therefore phosphorus is greater than strontium. You can do something like that, all right? But the long term is you have two good things happening. You have more Harrison Fords and you have fewer shells. So it's a win-win situation for phosphorus, okay? So how does this relate to atomic radii, okay? Well, folks, I've been around for a few years, probably more years than I like to admit. And as a teacher standing out in the hallway, do you think I can tell which couples have greater attraction for each other? How do I know that? Just by observation. I can see how they stand towards each other, all right? I can see how closely they walked with each other. Their personal space has shrunk if you're attracted to that other person, okay? If you don't know someone, a complete stranger, or you really don't like that certain someone, don't you stand a little further away? Yes, okay, so that's the same thing that happens here, okay? So the greater attraction, the more those electrons are being drawn to that nucleus, the smaller that radius. The radius is truly defined by 1/2 the distance between the nuclei of two adjacent atoms. That's a long verbiage there. But really what we're looking at is how far away is it from the nucleus to the outermost electron, okay? And the official definition is why the values for your noble gases are a little bit skewed. The problem is you really can't get those noble gases too close to each other to see what half the distance is. So like I said, they're a little bit skewed if you look at your graph. But if you think about the distance between the innermost, or sorry, the nucleus and the outermost electron, that's going to really it's really define atomic radius, okay? So let's check this out here. Here's a graph. Oops, hang on. So just looking at a graph like this, as you go across the period, the atomic radii does what? Well, just look, all right? It's getting smaller, isn't it? So why do you think it's getting smaller? Well, what do we know as it go across the period? Look at your periodic table with Harrison Ford on it, all right? You have more protons in that nucleus, therefore you have greater attraction. And what happens? The electrons are being drawn into that nucleus, so the nucleus or the atomic radii gets smaller, okay? That's pretty awesome there, isn't it? So I wrote decreases, there are more protons, therefore greater attraction, therefore the electrons are closer to the nucleus, the radius goes down, okay? Good news for that electron, okay? So what if I go down a group? Just look at the pictures, for heaven's sakes. What happens? Obviously, the atomic radii gets bigger. Why? There's more shells. There's greater distance from the nucleus. There's less attraction. There's more space in between those electrons, the outer electrons, and the nucleus. So obviously cesium in this chart is the largest atom. Hey, which is your smallest atom? And here, it looks like it's helium, isn't it? Up here, that's helium. So this gets big. This is really, really, really tiny. Okay, so if you look at these numbers here, hydrogen's 37, probably picometers, and there's helium at 31. So 31 is smaller than hydrogen. Those two protons are drawing in the outermost electron to be even closer than one proton will. Okay. I'm going to stop here for now. Look for part 2. Okay, so I'm going to leave you with this thought. Okay, hey guys, don't wait to be great. Take care.